Going to begin week 3 by finishing off chapter 3 and the portion on scientific studies. First, we'll do a quick quiz review. Here you can see the question on mean, median, mode, and range. So the mean was 15.75. The median was 16.5, but if you put 16, 16.5, or 17, I gave it to you. The mode were 3 numbers, 15, 17, and 18, all appeared twice. The range was 8 to 21, and the range value was 13. There was confusion with the range and the range value, so everybody received 1 point back, regardless if you got it right or wrong, on the range and range value. Going forward, we're going to just use the range as one number. So if I would ask you what the range is, you would subtract 21 from 8, and the answer would be 13. Another one where there was slight confusion, not a lot, was between odds ratio, and relative risk. I wanted to make sure you all understood what they truly meant. The odds are the likelihood that an event will or will not take place. The odds ratio is the quantification of the association of two events. So it's the odds that two events are associated together. And relative risk is the ratio of the probability of an outcome in an exposed group to the probability of an outcome in an unexposed group. And then differential justice. Got a lot of answers on this, and pretty much everybody was around the societal aspect of differential justice. Differential justice it's not just social. A lot of people had correct ideas of how of giving me that the African American and Hispanics are treated different within the justice system. However, it can be applied based on past performances. So you have the 3 strikes rule in Illinois. So if I have committed crimes before and I commit the same crime as you, and this is the first time, differential justice, I'm going to be punished harsher than you are because it is your first offense, where it is my multiple offense. So if that question does come up again, just remember, it's not all social aspects of justice. It also has to do with past performances. So today's goals, we're going to review the different types of scientific studies. We're going to provide tips on how to evaluate them, talk about what's behind the numbers, and review news reporting of scientific studies. That's very important to be a healthy skeptic, and we'll get into that a little bit here later. So scientific studies, caveat emptor. Caveat emptor is let the buyer beware, or in this case, you want to be the reader. You want to know more about what the study's about, who did it, why they did it, who funded it, and we'll get into this a little bit later. Being a healthy skeptic is not dismissing everything outright, but it's a tactic to use to, if you feel that, or you hear something and you feel that it may just not be that, that's healthy skepticism. Outright disbelieving anything you hear is being one-sided. And there it talks about news outlets like to get attention through big headlines. Fear and violence, they sell news. I hope that's not shocking to some of you. But fear and violence sell news better than scientific rhetoric or explanation. So a lot of what we get from the news might not necessarily be the whole story, and it might be one-sided. And you can see a lot of this in the political arena. You have certain news will fit within a certain demographic, or a certain channel will have their story geared one way, and if you go to the other channel, um, and it's the exact same story, but they'll be uh, posing it in a completely different light. So you have to take news from certain venues with a grain of salt. And if you feel strongly about it, you should find other corroborating um, news sites or documentation that backs up what they're actually saying. So you can make intelligent decisions, especially when it comes to risk. Currently going on right now, you have Hurricane Dorian down on the East Coast. Um, and it's a huge risk for people right now to whether they decide to stay in their homes or they decide to leave. Even though there are mandatory evacuations, they can't really force people out of their homes. But what a mandatory evacuation basically says is that if you don't leave on this day, there's going to be no community support. There's no police, there's no fire, there's no rescue until after the storm breaks. So, depending on where those people are getting their news, whether it's from local weather or national weather or the Weather Channel, um, they are making a decision whether or not to stay in their homes or not. So if they're getting their news off of Facebook posts and calling that the word of law and making the decisions based off that, they're not making intelligent decisions with a good amount of information. So I do like this. It's a nice political cartoon from the Cincinnati Enquirer all the way back in 1997, and I feel it's still relevant today. But it's random medical news, and as you can see, that we're just spinning the wheel, and we're saying that coffee can cause depression in twins, and they're just reporting that with no backing. I feel that we still have a lot of this today, especially when it comes to medical stuff. Some of you have been around for eggs. Um, Eggs were bad, then they were good, then they were bad again, and now they're good again, but only if you eat part of them. Same thing goes with coffee. Coffee is another one that has been good, has been bad, has been good, and now it's there, and now they're saying, well, coffee itself is not bad for you. It's everything you put into it, which makes a little bit more sense if you just logically think about it. Coffee's an active stimulant. It helps with the digestive system. It's got caffeine in it, and if you just drink it black, that's all you're getting. But when you start adding creamers and you add sugars, you make uh, you're potentially making coffee more unhealthy. And I think that's where a lot of these studies stem from, is that um, we were looking at coffee as the base, but not taking into account that somebody may be adding half a cup of sugar to every cup of coffee, or somebody's using whole fat creamers versus somebody that's using skim milk, and we're lumping it all together. And that, again, informed media is very important. So, news reporting studies. This you have this article. Take a look at it. Uh, think about it. It's linked in this week's Reginet, but it's about laser printers, and you see that title: laser printers may pose health risks. So just taking a look at that, we have the cause, um, laser printers, and we have the what is health risks, and we're saying may. So the word may, could, maybe, all in headlines should lead you to think maybe I should read more into this and see what they're saying. And what this news reporting, or this study, this is a study, is that the emissions from office laser printers can be as unhealthy as cigarette smoke, according to an Australian professor who's now calling for regulations to limit printer emissions. So if you actually read through the study, um, and we'll get to it, but a little bit later, as you read through the study, he doesn't specifically really measure anything, and we'll show you. So from this, and this was in August of 2007, when this was done, you had several other news outlets pick up the story. Office printers emit dust particles which are as bad for you as smoking. Office printers are health risk from BBC News. So uh, we start picking up the news story, and as more and more outlets report it, more and more people think, well, if I keep hearing about this, it must be something. Well, here's what the study said. The highest printer particle emission rate found in the chamber was very, very small, which is close to the median value of submicrometer particle number emission rates for activities such as cigarette smoking occurring in residential houses. What this is saying is that the largest printer particle number that was emitted is close to the same median value as cigarette smoking. So the 2017 study didn't identify any types of particles, just the size of them. And it also discounted that other sources of ultrafine particles include candles, home cooking, and fires. Um, and so this study, if you really get into it, it shows that the printers produce particles. The printers producing the particles is not the same as showing uh, a health effect. So 2 years later, follow-up study. Particles are aerosol condensates of volatile organic compounds. Follow-up to study done 2 years later. The particles are aerosol condensates of VOCs, which are volatile organic compounds, and semi-volatile organic compounds. Um, So health effects relate to VOCs and SVOCs and not to particle size. So this study is saying that um, laser printers were off-gassing, for no better term, VOCs and SVOCs, and regardless of their size, the VOCs and SVOCs can be an irritant to breathing and contribute to poor indoor air quality. This study was done much more thoroughly, and it gives a better answer to, well, they're the same size of everything else, so they must be bad, because that's basically the first study on what it said. So this brings us is, why are scientific studies important? Well, they are enhance our desire to learn, and they back up that learning with facts. And you get a lot of times you'll get distorted information or inaccurate reporting in the news, where scientific studies are held to a higher standard. That most of them are vetted thoroughly by other peers inside the profession. Most of you have heard of a peer-reviewed study. That means that the study was done and then it was sent out into the scientific world for other scientists or other uh, subject matter experts on whatever the study was to verify that it was a good study, that it is um, reliable, and that the information is in fact correct. All of these lead to credible and reliable sources of information. So this, what we see on the screen, is not a reliable scientific study. Drug companies fear release of the new aloe cure. Big Pharma stands to lose billions as doctors recommend drug-free health cocktail that adjusts and corrects your body's health conditions. Many of you have had to have heard of this, whether on the radio, seen an ad on Facebook, seen an ad on TV, seen an ad anywhere about a miracle drug or a pain a pain reliever that's all natural, um, or an advertisement for a supplement that just seems too good to be true. And a lot of this advertising is exactly that. It's too good to be true. So when you see something like that, you want to ask several questions. One, who wrote it and who's talking about it? So in this specific um, example, who's this David Waxman and who is Dr. Lisa Leal? Um, Ask who they are, what and look into what they've done. Are there studies? Have there been studies been done on them? If there have been studies done on them, where are the studies? Why aren't they giving you uh, the study? And you can see up in the upper corner here where it says "Unleash your memory." Studies show that your brain needs a healthy bacteria. Well, what study? They should provide you the resource that they're citing. Uh, how has this product been tested? Testing is very important, and we'll get that in a minute here about the different types of testing and why, which ones are good and which ones are used for which are better than the others. And then you also look who funded this. If it's a study that's done on the dangers of smoking, and as you get into it and you realize, hey, this study's kind of downplaying smoking. Well, many studies have been done really since the 1950s on the health hazards of smoking and what it does and its lead as a cause of lung cancer. Well, if you happen to see a study that maybe downplays the lead that it's a cause for lung cancer, look and see who funded it. Is it one of the big tobacco companies or a company that's related to them? Because who's paying for it can skew how the data is represented in the end, because they want to make the people that are paying the bills happy. And then finally at the bottom here, always look for one of these. These statements have not been evaluated by the Food and Drug Administration. This product is not intended to diagnose, treat, or cure, prevent, or any type of disease. This is a big one. If it's especially if it's a drug or some type of new medication or a supplement. Supplement's a bad word because most supplements have not been evaluated by the Food and Drug Administration. Um, but any type of medicine that's going to go on the market through, especially prescription wise, has to be evaluated by the Food and Drug Administration. Supplements and the healthy living style, organic, holistic. These are all words that show up on packages at GNC or at Walmart. They may or may not do what they say, and they don't necessarily have to list the ingredients that are inside them um, to be able to be marketed as a health um, supplement or a health tonic, if you will. So, what is a scientific study? A scientific study is a process of answering a question using data and evidence. There's two types of health-related studies. One can be descriptive, and the other is analytical. Descriptive uh, studies describe health-related events by person, place, and time. Analytical uses a comparison group to identify causes or risk factor. And then there's observational studies that look at two different populations, and there's experimental, which a lot of the medicine that we talked about with the placebo effect last week. Experimental is where two groups receive different levels of intervention. And that would be giving one group a placebo and the other the medication, uh, and seeing which, uh, if there's any actual benefit to the medicine over the placebo. So, questions to ask again: who funded the study? Again, who's paying the bills is important. One of the things, from my experience, a couple years ago, the the ASSP student section at Illinois State did a anti-fatigue mat study where we had 3 different types of anti-fatigue mats, took them around to some of the offices around campus, and had people fill out surveys, and then we collected the data and we made assumptions based on the data we collected, and we made statements based on that. What we found out, what actually I found out, was that as we would go, we presented twice at 2 conferences, and at both the conferences, people were highly interested in our study. And one of the reasons is because we are a public university, so we are um, we were a third party, not interested in anything else study, uh, and so people wanted our data because then they could say, here's a study done that shows these types of mats are the best according to their study, but we're third party, we're disinterested. Whereas a lot of other companies, especially with ergonomics and like flooring or mats or a ball peen hammer, the study's done funded by that company. So they want their product to look better. We were third party, disinterested in, we just wanted the data. And people wanted our study because of that. How was the research question worded? Research can be worded vaguely, so as your data comes in, you can play around with it, manipulate it, if you will, um, to answer the question that makes more favorably. How was the quantity measured? Again, what type of measure are you using? Were your measurements accurate? Was it the best way to measure it? What was the time period? Was it very short or is it long? Uh, did you do a study that lasted 3 days and you're saying, well, there's no effects of this on a person's health because hey, we did a study over 3 days and nothing happened to them. What are the limitations? Did you The limitations of a study are important because what you're limited by actually will kind of define the scope and how in depth your study can get. Um, and we just talked about this, but have your results been peer reviewed and peer reviewed publications? This is, again, it's very important. You do a study, then you send it to like minded people. They review your study, and they actually write um, notes on it that are not necessarily given back to you, but are given to publications that say, I agree, the study is well done, it, it is kosher, it's ethical, there's no questions about it. Or it could be to the point where it's bad. The study's just bad. The questions don't get answered correctly. The data doesn't seem to be matching up to what your conclusions are. And they could send and say, "Hey, public. I would not publish this just because it's questionable, and I don't think that the uh, your magazine or your journal would have any positive reaction from it." So, sorting out your facts of a study, survival statistics often used to encourage medical screenings. So, screenings are important, um, and they're used in lots of studies, but a screening doesn't necessarily uh, contribute to causation. So you look at the 3 screenings there: mammography for breast cancer, colonoscopy for colon cancer, and PSA testing. So then you have these screenings, and then you have 5-year and 10-year survival statistics. But what screening does is if everybody goes out for a colonoscopy, so I believe right now the age of 40. Once you get 40, they start doctors will start screening for potential for colon cancer. Um, but if you took that time frame and you moved it from 40 to 30 or even to 25, and you said, well, we need to get a colonoscopy at the age of 25 to prevent colon cancer. An earlier diagnosis is always going to increase your survival rates. So when it gets into screenings, you want to look at the data clearly, and but screenings are important. Don't forget that. But the statistics overstate the benefit, and this is how. So here's without screening, 10 years. So you got 1,000 patients with progressive lung cancer. 10 years later, there's only 50 alive. 950 of them are dead. It's got a 5% survival rate. So with screening, 4,000 patients with non-progressive lung cancer, 1,000 patients with progressive lung cancer. So this is with screening. You had 5,000 people come in for a screening, and 1,000 were found to have lung cancer. On the back end, 10 years later, 50 are alive, 950 are dead, 4,000 are alive. So the screening would say there's 4,000, plus people that have lived because they got this screening. But the survivability rate is still only 5%. So the same 50 people died regardless whether they got their screening or not. But if you look at the survival rate now with the screening, the survival rate goes clear up to 81%. Again, 5% with the actual disease survived. But because you said we screened 5,000 and only 950 died, the survival rate goes clear up to 81%. So when screenings are used, you got to be skeptical of the way they're using their numbers. So again, what kind of science is behind the numbers? So in this little chart here, from the bottom to the top is the strength of evidence. So the stronger evidence is at the top. There's laboratory animals, there's human studies, there's case control studies, cohort studies, and all the way to the top we talk about meta-analysis. But these are the different types of studies that you can be doing. And so we're going to cover these. So your laboratory studies. So you have in vitro and in vivo. In vitro is test tubes or similar lab equipment. So for those that have taken any biology classes, you do in vitro research. Whether that's growing bacteria or growing viruses, it's all in vitro. You're doing it in a test site within test tubes and using lab equipment. In vivo is done in a living organism. So mainly that's done in animals, and this is where you get into giving an animal something and studying what happens to them. And animal studies are we generally go for the lethal dose, and the LD50 is the amount of material that will kill 50% of laboratory animals, and it's expressed in milligrams per kilogram of body weight. So with rats, as you can see here on the side, we'll use the top one, which is sucrose, is table sugar. So they, out of 100 rats, and we're using rats just as an example, out of 100 rats, they gave each of them 29,700 milligrams of table sugar, and 50% of those rats died from that. That is what the LD50 is. And so as you look down here, so mercury chloride, 1 milligram of mercury chloride killed 50% of the laboratory animals that it studied. That it was given to. So why large doses in animals studies? Well, to be accurate, millions of animals would have to be used to get representative rates. Uh, basically, the life of animals, if you gave them small doses and then waited, um, they don't live long enough for something to have that great of effect on them. So instead of having these large million volumes of animals um, and keeping them for years, you give hundreds of animals megadoses over their short lives. So you can see what type of effect and see if it has any type of correlation to the human body. So with saccharin, which is a sugar product, you have tens of thousands of cans of diet soda would be given at one shot. Um, and saccharin, for those that you don't know, I believe is the artificial sweetener that was in diet soda in the beginning that became linked to types of cancer. So to study that, they would give the equivalent of 10,000 cans of diet soda of saccharin to a laboratory animal and then wait and see what happened. Animal studies aren't that strong though. Animals aren't humans, so the effect that it has on a animal doesn't necessarily predict the same type of effects on humans. And so we'll look at cyanide and thalidomide um, down here. Cyanide, if you take it as a human, will kill you pretty quickly too, especially the higher the dose. It has no effect on rats, and there's little effect on rats with the thalidomide, um, but in humans there's widespread birth defects. So again, you don't know what animal is going to be the best indicator of human effects. You don't know what drug may have zero effect on a rat, just like cyanide, but is deadly to a human, and vice versa. You may give something to a rat that just, I mean, it's 100% deadly, but then with humans, it has no effect. And so all this testing, what it does is it leads to so your dose response. We're going to get into toxicology a little bit here, but so the dose response helps determine three things: causality, threshold, and the slope of response. So with causality, a chemical induced observable effect is what a causality is. So the higher the dose is given, uh, will show some type of effect. And what we're trying to gather is the threshold. And the threshold is the lowest dose where an effect occurs. So we get into the dose size, we get to the lowest dose where there's a effect that can show causality. And then the slope of the response is it's for dose response, and it's the rate at which the injury builds. So you could have a low slope where as the dose increases, the injury or the health effect slowly builds up, or you could have a steep slope where given lower doses, it compounds and it just shoots right up there. So you can have a threshold level of, say, 1 milligram, and you say, okay, at 1 milligram, we're showing this type of cancer. That's your threshold. But then at 2 milligrams, it spikes up to a high percentage that you're going to get the cancer or a high effect, and that would give you a steeper slope. So what kind of science is behind the numbers? And this is gonna what we're gonna move on to is the studies, all the different types of studies there are. So human studies, they're observational, uncontrolled study. You can watch what happens to one group of people. Anybody can do this. You can go take a seat in the quad and just observe people, and you're conducting an observational, uncontrolled study. You put nothing into place. You have an observational controlled study, and this includes a control group and it can be with or without your personal intervention. And then you have randomized control trial. Two groups are very similar, placed in a trial or control groups by random selection. Multiple randomized trials provide even more reliable data. So you have two populations, let's say 50 people, and these two populations are very similar to each other, and their names are all put into a hat, and then they're randomly drawn out, and now you have a control group and a trial group. That is randomization. Uh, and then we'll get into double blind a little bit later here, but the double blind would be the next step. So case control is what we'll start off. The case control starts off with people who have the disease and who do not have the disease. Uh, so as you look at this diagram here, or this graphic, uh, you're trying to link exposures to different risk factors. So the cases that have the disease, you ask them what kind of exposures they had, when they were exposed, for how long, and same with the controls. And what you're trying to do is you're linking um, these exposures to a specific thing and trying to find a potential cause of a disease. Uh, so what you get out of this, which we've already covered, is the odds ratio. So you have the odds of being exposed, which is your cases, divided by the odds of it being exposed, and these are controls. So we're talking about a specific exposure. So if this number is greater than 1, the odds ratio is larger than 1. It has an association with the disease. If it is less than 1, it's actually a protective number, meaning that whatever that exposure is potentially preventing the disease. And if it is exactly 1, there's no association um, whatsoever. So remember, the odds ratio is of 1 exposure to the cases and the same exposure to the control group, and you get the odds ratio. So as we can see here, case control studies have some advantages. They're quick and cheap, and they're good for uncommon diseases. The disadvantages, they're not good with rare exposures. Control selection is sometimes hard. And since you're asking people to remember whether or not they've been to had certain exposures to something, recall could potentially be an issue. Our next study that we're going to cover is a cohort. These are groups of people that are followed over time, and generally these last for years. Um, these look for risk factors, and this is measured in your relative risk, which we covered last week. So the difference between cohort and um, the control studies is that the cohort, you have an exposed group and a non-exposed group, and then you're watching and waiting to see if a disease develops. So control studies, I'm sorry, case control start with the disease and try to find the exposures, where cohort studies start with exposed people and see if a disease develops. So there's prospective and retrospective cohorts. Retrospective starts in the past, as we can see here, and goes forward, where prospective starts in the now and tries to say over a period of time that exposures will lead to um, a disease. Now, these are, if you're doing a prospective or retrospective cohort, it's non-randomized. You're picking the people, and you're picking whether or not they're exposed or not exposed based on how they are as people. So the advantages of a cohort study is a time sequence can be determined. So you can find causality. You can say that this person over 10 years was exposed this many times to this and only this, and it caused this disease. So you can link exposures to specific diseases. You get a collection of outcomes and risk factors. So basically, over the time of the study, you're collecting all of this data on people and all the different types of exposures they get. So these exposures build up. Well, now you have a sub-analysis. So you may be able to eliminate some exposures and say, well, this does never cause this before, but these potentially could have. These exposures could have, and now you have sub-analysis within the study. The disadvantages, it's the cost. They're very costly. They're very lengthy. They need to be. There needs to be manpower, uh, and there needs to be monetary resources given to a study because of the length of time. It's not good for rare diseases, um, and ensuring people who started the study stay till the end. One of the issues that cohort studies has is attrition, and that's whether people die or they just fall off the face of the earth or they get out of the study because they don't want to do it anymore. That is one of the hard things about cohort studies as they try to manage people over such a long period of time. Comparison of the cohort and case control studies. So we just covered this, but as you can see, a cohort, it starts with an exposure, and a case control starts with the disease. That's a very important fact that you should remember. You should know the difference between these two types of studies. Clinical trial and an intervention study. So, an intervention study or a clinical trial is much we've probably heard of more than intervention study. It deals with medicines, vaccines, and even health advice. What it does is it's, as you can see, you have a randomly assigned treatment group, whether it's a new treatment, current treatment, and you see who improved and who did not improve. So with the current treatment, that could be no treatment. So you could have a no treatment group and a new treatment group, especially if you're just bringing a drug to the market and you want to study it. Then the positive outcomes, they look for a change in the behavior of a person. They look for change in a disease status. Um, and along with these intervention studies, you get into the randomized double blind studies. So this is what we were talking about earlier. You're randomized that participants are either in an intervention group or a control group. And if that's done by somebody outside of the researcher or the participant, it's called a double blind. That way, the researcher themselves cannot have any bias into how they're studying a certain group of people, or are they giving more care on one side than the other. Um, you can get into certain ethical dilemmas with some of these clinical trials. Um, so again, not doing an intervention may be considered unethical. Your advantages are good evidence of causality, and randomization gives equal chance to, and the groups are very similar. Um, the disadvantages is that these are really expensive. They have many participants, and sometimes they're not always possible. Some of your ethical things as a researcher, if you're doing a clinical trial, is that you may if you're not doing double blind, you know who's getting the treatment and who's not. So you may feel that you need to give the treatment to somebody else. Um, over another person. That's why the double blind is very important in these studies, especially when children are involved. If it's a trial for maybe childhood cancer, um, you feel everybody should get the treatment, but not everybody can. due to the expense of it, or you just wouldn't get enough data. So ethics can come into play on clinical trials. Some families are desperate for hope and are willing to do almost anything to get a treatment. Meta-analysis. This is the last type of study that we'll cover here. So meta-analysis combines the results of previous studies. So you take studies of all similar design, you data process it, you do a combined analysis, and you get a single summary result. So if you look here as an example, meta-analysis odds ratio, 95% confidence interval for 9 U.S. epidemiological studies that hypothesized association between exposure to environmental tobacco smoke and lung cancer. So there were 9 different studies that did this. The meta-analysis computed all their data together, and you look here at the bottom, all 9 studies, there's an odds ratio of 1 to 1.5 roughly, that if you smoke, uh, or I should say, if you're exposed to environmental tobacco smoke, you have 1.5 chance odds to get lung cancer. This is always an important fact. Correlation does not imply causation. So just because something correlates together doesn't mean it's the actual cause. Um, this is an important concept for you safety majors, for you anybody going into health sciences. Correlation does not always imply causation. Go back to our the first time we talked about heat stroke and ice cream. Uh, because it's hotter outside, people buy more ice cream. Also, because it's hotter outside, there's an increase of heat stroke. Just because there's a correlation between heat and becoming a heat stroke victim and eating more ice cream doesn't mean that ice cream causes heat stroke. So always keep that in mind. So to further aid you in this, there's a video on epidemiological studies. It is linked in here. It's very it's an overview of a little more in depth of what we did. So if you would like to learn more about studies, please watch the video. Nothing out of the PowerPoints. Um, I'm sorry, nothing out of the PowerPoints come directly from the video. So it is just a little bit more in-depth look at the studies.